All right. Good morning, everybody. Thank you for coming to my talk on Internet of Things RF software-defined radio. I'm Kevin Bong. I'm a penetration tester. I work for a company called Sikich. Aside from that, I'm kind of a hardware hacking hobbyist, so I work with Arduinos and routers and things like that. One of the projects I've done, it's the Mini Poner. It's a penetration testing Dropbox. So if you go to the Mini Poner website, you'll see instructions to build a router into a penetration testing box. And I work with Michael View here, one of the other folks from Sikich, who will be giving a talk at noon on biohacking. But we co-host a little Mayhem Lab video blog with different hacking projects and things like that. I work for Sikich. We're a we do auditing, we do financial stuff, we do all the security stuff. If you're looking for a job, we hire security people. So they're paying for me to be here, so that's their shameless plug. And with that, we're going to jump into the talk. So this talk is about radio frequency analysis, kind of first steps into it for people who haven't done anything like this before. I was kind of here about a year ago when I started buying gear and playing with it. And it seems really daunting, and it seems kind of expensive at times and things like that, like how do I get started and things like that. So what I tried to put together here was a talk that's great for, like, you know nothing and you might want to get interested in this, and how can you do that? What are some experiments you can do? They're pretty cool, that are pretty inexpensive, and that kind of help build your knowledge on these topics. So there's simple examples, but they give you the foundation if you want to do more in-depth kind of analysis, kind of building off of this. And so with that, we're going to start with radio signals. When you're working with this stuff, it's helpful to have just a basic understanding of how radio signals work. And this was a graphic I found on the internet that was pretty good. You think about that gray bar there as an antenna that's doing being a transmitter. And so the lower part of that bar there, you'll see an orange dot just going up and down, making a sine wave. Well, think of that think of that as a packet of electrons that's getting pushed up and down that antenna. And by that, electric field going up and down the antenna, it's creating this magnetic field, electromagnetic field that the antenna radiates, which is your radio signal. So that's just the basics of it. And then the example they have on the top is where you're modifying that basic sine wave to have a pattern to it. And that's what really radio signals are. They take this just basic sine wave and they either compress it this way or compress it this way to make a radio wave out of it that has information in it. When we're talking about radio frequency analysis, there's really two different types of ways that people overlay data over that basic radio signal. So at the top here, you see that basic radio signal. The first way is called amplitude modulation. You're just changing how strong that signal is as it gets radiated. And you see the middle there, it's like, strong signals, weak signals, or in some cases people even do amplitude modulation with kind of an on-off keying. You turn the transmitter on, you turn the transmitter off, you turn the transmitter on, you turn the transmitter off. It has the same effect. FM modulation is a little more interesting. Instead of changing the amplitude, you're changing the frequency of the signals. So your basic frequency is going to be just a pretty, what you'd expect to see for a sine wave, but it would encode potentially a 0 as compressed waves, slightly faster frequency than that, and 0 as 1s as, expanded waves, slightly lower frequency. So those are the two modulation types that we'll be working with as we look at some of these demos. And then we're going to do how does a radio work, and then how does software-defined radio work. So when you look at a radio that receives these signals, you're familiar with an antenna, just something that is shaped and structured and sized right to best catch that frequency of radio signal and feed it into the rest of the thing. Those signals are traveling through the air. They're not very strong, so typically the first component then of your radio is some type of amplifier to take that weak signal and make it stronger so that the electrical components inside the radio can actually do something with it. It's not so weak that they don't see it. After that, you've got a tuner, so that says, okay, well, this antenna picked up all these different frequencies, but I only want to look at this frequency. And that's what the tuner does. It filters out the frequencies above and below that one frequency that you're looking at, or if it's like that frequency shift keying, it's actually kind of a range of frequencies that you're looking at in there. From the tuner, it goes to the detector, so that's the part that has to understand, is this frequency modulation or amplitude modulation, and based on that, how do I decode that overlying signal from this, radio signal? That's what the detector does. And then in a typical radio, it's an audio amplifier. We're going to see how a lot of the digital signals really are very similar to those audio signals, but instead of an audio amplifier, we're sending them into something else to process that digital signal typically. So what is software-defined radio? Well, software-defined radio is where we basically take all these things. Typically the amplifier is going to be in hardware, but you can take the tuner, the detector, all those different parts, and you put them in software. Now we have computers and embedded systems that are strong enough to take all that data of all these analog signals and figure it out. So that's really what the software-defined radio does. I've got two common examples here. The first one on this side, I don't know my left and right, is what we're going to be using for these demos today. It's referred to in the software-defined radio software space as an RTL SDR. It's because it's based on a Realtek RTL chip. But these are really popular because they're super cheap. We'll talk about that in a second. And it's only a receiver. It just receives transmissions like a radio would. On the other side there is a hack RF. There's a lot of different things. I happen to have a hack RF, so that's why I put it on the slide. That runs about $300, but it gets you a much wider range of frequencies. It's much more exacting, and it has a transmitter, so you can actually produce radio signals as well as receive and analyze them. So we're talking about this RTL SDR dongle, and I'm going to pass one around because it's kind of like. So what this is someone came up with this dongle to be a TV receiver that you plug into your computer. So you plug it in a USB port and you get digital television signals. Well, somebody else figured out that, hey, the chip that's inside there can get more than television signals. It can actually get a pretty wide range of signals. And I can rewrite the program to have it do that for me, and I've got a really cheap software-defined radio. So they've become really popular for that purpose. Different models, different people building them, different designs have different ranges in frequency, but typically you're looking somewhere between 24 megahertz and 1100 megahertz. So if you're thinking about your like Wi-Fi, which is 2.4 gigahertz, that's 2400 megahertz. That's going to be outside this. Or like an RFID that's 125 kilohertz or 13 megahertz, that's going to be outside of this. But a lot of the other stuff that you think about in terms of like, we'll talk about pager traffic, we'll talk about just standard radio stations, things like that, fall within this range. So it works for a lot of different things. And I was just talking to some of these, but some of the frequencies that it can see, 900 megahertz, you hear 900 megahertz all the time because when you buy a cordless phone, when you used to buy a cordless phone, who has a cordless phone anymore, it came at 900 megahertz, your baby monitor, things like that. So frequencies are established by the FCC about what you can use them for. So like 900 megahertz, there's some ranges in there that are free, are available for us to use unlicensed, so we don't need a license to use those. That's why it's used for things like cordless phones and pagers. 450 megahertz is a licensed thing, but there's ones in there commonly used for your law dispatch or EMS. So if you've got like if you want to do trunk tracking where you're police scanning, that's in that range. 433 megahertz is one of the license-free ranges. It's really commonly used for a lot of like low-power Internet of Things devices, thing like a wireless doorbell or the wireless thermometer that I've got outside that I can read on my wall inside is at 433 megahertz. Car keys, things like that, commonly run in that range. Not all of them, but a lot of them. 160 megahertz is your NOAA weather radio, and then even when you think about like mix 99.1 is actually 99.1 megahertz. That's where you're going to find it in the radio station frequencies. So with the Mini Poner project, with all of our hacking projects, one of my big goals is to do it cheaply because I'm cheap and because when you get to hardware hacking, sometimes you can break things. So I really love this project because you can do it super cheaply. And here was my shopping list. If you're not familiar with AliExpress, I've bought so much stuff from AliExpress. People are, it's like the Amazon of China, and the prices are disturbingly cheap. I don't know how they do it. But so for example, for free shipping, $8.80, get the radio that we're using here. I'm using an Arduino Nano. We'll see the circuit for this in a minute, but that was like under $3 shipped. Nano clone, I should say. The transmitter and receiver that we're going to be using, $1. We'll talk about that. And then the other components, the only other parts I'm using is a proto board to plug the Arduino into and the transmitter and receiver into, and some jumper wires. So under $15, you can duplicate what I've done here, like skip a lunch at a restaurant and have some fun and learn something. So you buy that software-defined radio and you want to go and plug it in. You can run this on Linux, you can run this on Windows. If you're gonna, and on both sides, the biggest catch is that it was designed to be a TV tuner. So when you plug it in, your operating system is going to say, "Oh, I've got a TV tuner. I'm going to load a TV tuner driver," because it's so helpful. So if you're on Windows, the first thing you need to do is get this, I don't know how to pronounce it, ZADIG program, and replace the RTL 2838 driver with this just generic WinUSB driver. And then it's just a standard USB device that can transmit data, and the operating system lets your software use it. Similar on Linux, there's actually packages for the RTL dongle, for the other software you want to use, like GNU Radio. We'll talk about some of these software packages. But very similarly, it's going to try to auto-load its TV USB driver, so you need to blacklist that USB driver kernel module, and however your flavor of Linux wants you to do that. But once you've done that, hopefully everybody can hear me once I move down here, because the rest of this is basically going to be demos. Once you do that, you'll have a program. This is the program called GrrCON. It's a graphical control for that software-defined radio dongle. If I go look at my IO devices, you can see it's using that generic radio dongle, just default settings here. But what it lets me do then is I can basically...
Center in Grandville. Find us on Facebook and online.
So what you see in this, this area here is called a waterfall, and basically it's showing, like, this is the range that this dongle can see from this frequency to this frequency. And within that range it sees this, this yellow signal. Oh, that's probably an interesting signal. This blue stuff here is static. Here's a really weak signal. And I also see, well, I know because this is like 95.6, it's probably a radio station. So I've set my mode here to FM. If it was an AM radio station, I would choose AM. And then just center on that frequency, and as you heard, because I wasn't really paying attention to what I was doing,
turn to Jonathan Stevens, who makes high-quality mattresses right here.
Pick this up and drag around to see if I can see another station. So this is kind of the hello world for using your dongle, is if you can get to the radio stations, things are kind of working. Some other interesting things here in this interface, once you get it kind of started, you saw I used the start and stop digital, I can stop receiving data, I can start receiving data through the menu here. There's also a button in the toolbar that I hid because my resolution's messed up. Other things I can do, if I want to change the frequency, it's kind of a weird interface. If I want to go to 86, I actually click on the lower half of the 9 and kind of up and down that way. But you can see it's jumping to the different frequencies then. There's nothing in the 86 band, but I can start looking through, are there other signals that would be interesting? This might be a radio signal here, type of thing. You've got a couple different controls over on this side. So I showed you the one, I'm right now in the receiver options. I showed you the one where I switched it from AM to FM to some of these other options. The squelch, if you're familiar with the radio squelch, it's like at what point do you turn on or off the static, basically, whether you want to hear the noise or not hear the noise. Input controls, this is where you control how the radio is actually trying to analyze the data to some extent. The gain, you can see if I turn that up, it's seeing a lot more things as potentially interesting signals, and this almost turns red in the middle, and it will turn red on a really strong signal. If we go back to the local radio station, which I think was 95.7. Yeah, you can see it's red in the middle there for that one. So that helps you kind of try and tune things to see where the interesting signals are. I think it's, you get it where it's mostly blue here, the signals stand out that way. So that's some of the stuff that the tool does. So we've got our radio dongle working now. We just listened to a radio station, and that was pretty cool. We could go to other frequencies a little later in the talk. I'll probably start looking at, or have us take a look at like pager traffic, which I think is at 929. So you just saw this little blip here, that little blip there. So those are pager frequency, pager traffic, like the pager on your belt or whatever. And you can see it looks a little different. It's not that wide yellow kind of messy thing. It's all in a very stiff bar, and that's because it's amplitude modulation. Well, actually, this is frequency modulation. It's just a very much narrow frequency it's using. But also, if you've got AM signals, they'll be much more narrow like this because they don't change their frequency. They just change their kind of amplitude, their power. So that's kind of how we use this tool. And I'm going to stop that for now and kind of move on. One of the things I found when you get these RTL dongles, they can, they're cheap, so they might not be correct in their frequency. An easy way to figure that out is if I knew that the local radio station was at 95.7, I'd try and find that station and look at where where my dongle thinks it is, and just you'd have to do some math, or there's some a box in GQRX where you can correct that, so it'll correct that stuff. If you're doing more exacting stuff, like looking at definitely if you're looking at the GPS signals, you need much more accurate calibration, and there's some utilities for doing that. I won't go into that. So we saw the tool to view the graphical thing, and then there's a number of kind of command line tools people have built to intercept and decode things that exist. We'll look at pager traffic potentially a little bit later. Another interesting one that I found was automatic meter reading. So I looked at my meter, electric meter outside my house, and noticed that it was a newer one with some type of transmitter on it, which I figured because they're never walking up to my house anymore. They just drive by on the road. And so it was really easy for me using this RTL dongle to figure out how to read the meter, how to see what my meter's doing. The first tool we use to do this is a module of the RTL software-defined radio suite called RTL TCP. Basically, this just takes the data that's coming from the radio and spits it out onto a TCP channel, and it can also take commands from that TCP channel to say change the frequency or things like that. I'm just going to start it up with all its default settings here, and you can see it just said, hey, I've found a device and I've started listening, and I'm sending it out on port 1234. So all the default settings there. And I'm in TMUX here, so you're going to see me switch to a new session, and now I'm going to use another command called RTL AMR for automated meter reading. This is a tool I downloaded from GitHub and had to kind of do the whole make install, but that's all it took. But you can see here, I've paused it, so I'll keep it running. Typed RTL AMR, and it set itself to the frequency that it expects to find these automated meters at, and set the other kind of settings that it expected. And then you can see each of these things that's popping in is a meter reading. The ID of the meter here is 204-23821. It's even telling me if someone's tampered, if the tamper switches and how many times they've been tripped. And then here's the current consumption. So if I look at this for my house, I can say, okay, that's my meter ID. I can track my consumption over time just by logging this down at my computer downstairs. But the other interesting thing, as soon as I started doing this, is like, whoa, that's not just my house. There's my neighbor's house, the other neighbor's house. So I can start to see neighbor's electrical consumption, potentially even, like, is this interesting information? If I can correlate one of these IDs to a neighbor's meter, can I track when they're home, when they're not home, things like that. So that was just an interesting one, and it was just easy. 2 commands, and it's reading my meter from outside in my house. So that's kind of cool. And there's other pre-built tools or pre-built parts of tools that you can put together out there. Pager traffic, we'll see. APRS, if you're not familiar with APRS, it's a ham radio thing where folks on a certain frequency transmit interesting information in a certain format. Like, I've got it in my car, here's where I am, here's what I'm traveling, or they transmit weather, they transmit other things. So it's kind of a fun little project to receive that data. It comes with GPS coordinates, so you can map where all that data comes from. What we really want to talk about is, okay, so we saw like a first step how to receive signals and start to look at and play with them. But as pen testers, as a pen tester, my big goal next was, okay, well, I want to be able to understand how I might go about seeing a signal that maybe I see is radiating from a client's site, and go to analyze that, see what it is, see if I can figure out what it is, or if I can talk to it. A lot of industrial control systems might use radio things when you're doing a commercial client or industrial client or things like that. And we're seeing more and more, like, I call this Internet of Things, because like I said, a lot of those little cheap devices that people use that have to communicate don't use a full Bluetooth stack or something. They might use something like this. So to do this project, we're using this little 433 megahertz RF module. You'll see two devices there. The one in the foreground with the button on the front is the transmitter, and then the one in the background is the receiver. We'll focus mainly on the transmitter because we're going to use our software-defined radio as the receiver for most of this exercise. I do just want to show you how simple this transmitter really is. If you look at this area here, this one thing right here in the middle is a 433 megahertz crystal. That's this right here. So it's a slice of quartz shaped and tuned so if you start it vibrating, it's going to vibrate at 433 megahertz. And this circuitry around it is really just meant to, with these two inductors here, is meant to cause that to keep oscillating at that frequency. So it reinforces, yes, you should oscillate at that frequency, and here make yourself a little stronger and things like that. So that's what's happening here. And then the other big part of it here is you've got a data pin connected to an Arduino going through a transistor here that's basically acting like an on-off switch. And when it's on, this path to ground is open, and basically this is grounded. And when it's off, this path to ground is closed, and it's like it's not connected here. So you've got a really strong oscillator here oscillating at 433 megahertz connected to an antenna, and you've got something here turning this on and off to basically turn that signal on and off. So this is causing amplitude modulation. When the data pin is high and this is open, actually the data pin is low and this is open, it's going to, basically turn that signal on and off, like I said, kind of an on-off keying, and cause it to transmit or not transmit. So AM modulation, really simple transmitter kind of going on here. So then how do we actually make this do data? Here we use a library that's available for the Arduino called Virtual Wire. We'll look a bit more at what the library does in the background in a bit, but here's kind of all you have to do to use it. We pick out the transmit pin, so that's that data pin I was talking about. Tell it, kind of how many bits per second we want to send. Set up our message and use the library to send that message out the Arduino. So I've got one of these transmitters hooked up right now, and if you were to look at it, you could see that the little yellow LED there is blinking like twice a second. I've got it set to transmit like once or twice a second or something. So every time that blinks, it's transmitting just a little burst of data. So that's how I'm doing the transmitting. The receiving is very similar. The library does it the same way. I'm not going to spend time going into that because I'm going to run out of time. But let's take a look at how that signal looks in our radio then. So we're going to go back to GqRX, and I know that's 433 megahertz-ish, so I'm going to go down to that. And you can see right here towards the middle, we can see this. So what I'm going to do, so I know this is amplitude modulation. We'll switch it over to AM. And I'm going to turn the volume up so you can actually hear what that sounds like. So, really annoying. My wife gets annoyed when I'm like in the kitchen working on this stuff. She's like, yeah. So that's the signal. That's interesting. You'll also see this is a really cheap transmitter, so it's really noisy. So here's a second copy of the signal at a different frequency. and I could even, probably read it clearly way out here at other frequencies. But the strong one, the one it's actually transmitting at, is right there. So that's the frequency. Okay, well, if I'm seeing this frequency through the air and I don't know exactly what it is, the next thing I want to do is try to receive it and analyze it. We're going to do the kind of manual, simple, stupid way to do that, just so we understand how that actually works. And then that gets built into some of the tools that you've seen, like that command line meter reader. So while this is going, I'm just going to hit record here. Let it record a little bit. And then I stopped recording. So I recorded a few seconds, but certainly there were a couple pulses in there. Is that a 15-minute warning? What? It's an hour. 50 minutes, right? Anybody think I'm wrong? Yeah, we go till 11. Got me panicked there. All right, so I'm going to turn this off. So now, and you might be surprised by this, I'm going to go into Audacity, because that was just an audio file we just recorded. If you're familiar with Audacity, it's an audio editor. And I'm going to go open that file. I knew it was set to record here to the desktop, so there it is. And so if I play this and turn my volume up, which I'm not going to do, but you'll trust me, it's the right thing. I guess I will. Okay. But it's what we just recorded. It's that sound. So let's take a look at this. I'm first going to get rid of the stereo track, because I don't need both of them. And then, yeah, so there it is. So what happens if we zoom in on that and take a look? It's interesting. We can actually see the data. I can zoom in a bit further. And there it is. So that's the signal that the radio actually transmitted. We don't know what that signal means, but we actually know we have the signal now. We want to turn this into data. So to manually do this, one of the tricks that I've done is to grab a screenshot of that data, because it helps us understand kind of how would we analyze that as well. I'm going to grab that, and then paste it in here. So I've got it in a spreadsheet, stretch it out a little bit. And then if I can take these cells and squish them down, my computer's going to be slow. Squish them down so they're the same width as each of these signals. And through the magic of I've already done this for you already. So I basically squish it down, and it looks like it's even moved itself a bit. So that the cells line up with the start and stop of each signal. You can kind of see I've done that and followed them along. And then every time it's up, I'm going to make that a 1. Every time it's down, I'm going to make that a 0, 1, 0, 1, 0. So by doing that, kind of just look at the signal, match it up with cells, I get my kind of data stream, my raw data stream here. Still kind of meaningless. You'll see interesting here we see a lot of the same thing, and that's really common for a signal like this to have a preamble. Like I'm going to send just this oscillation to kind of let you catch on that I'm going to do something. So we've got an oscillation, and then we've got some data. Next question is, okay, what does that mean? Did I catch a signal? Does it make sense? Luckily, I made this signal. I know how it was made, so I can go back and see if does that make sense. Just kind of learn about it. So that's what we're going to do next. So we used Audacity to grab it. All right. So from the virtual wire documentation, it says each message is transmitted as a 36-bit training preamble. So that's what I said, that kind of just up, down, up, down, up, down. If we go back and count those, there'll be 18 of them, actually, 18 peaks, because there's an up is a 1, a down is a 2, that's 2 bits, up, down. So that's that 36-bit training preamble. And then we'd expect to see a 12-bit start symbol that's 0xb38, followed by the message length that's 2 bytes. Then they have this interesting thing. Everything after the start symbol is encoded 4 to 6 bits. Like, that's really confusing. What does that mean? So we actually had to go to the code to figure out what that meant. And what they've done is you've got 4 bits. If you're trying to transmit 0001, that's 4 bits there. That's not what they call DC balanced. You've got 3 zeros and 1 1. If you transmit a lot of those, you're going to have a whole lot more lows than highs, and your radio signal's going to be off. And ideally, your radio signal is going to be the best if you've got the same amount of high data on average as you've got low data on average over a short period of time. So what they've done is for each 4 bits, they actually use 6 bits, and they use these patterns to say, okay, a 0 actually gets encoded as 0xd. So if I had my calculator open, which I didn't think to do, I usually don't work on Linux, but I found that the software actually always works much better on Linux. Do I not get a binary mode on? What's that? The next one down? Oh, it's unscientific. That doesn't do hex and... It does? Oh, there, okay. Thank you very much. So if we just look at for a D, so we're going to go to hex D and look at what that is in binary. It's in 6 bits 0, 0, 1, 1, 0, 1. So there's an equal number of zeros and ones. And if we go back and look at this slide, the next one is 0xe, I think. Again, we're going to see 0, 0, 1, 1, 1, 0. So all 6 bits, you're going to have 3 zeros and 3 ones, but you've got to map these numbers then back to those numbers. So what that gets us then, if we go back to the, good slide first. So we go back to this, we're going to look for 36 bits training, and then the symbol 0xb38. So let's take a look what that is. B38. Look at that in binary. And that's interesting. So they actually use this kind of pattern, which we could pretty easily recognize, which is 10, 1100, 111000, as more of a training preamble. Did you get a real signal? So let's go look for that in our signal. So here's the training preamble end, and then I see 000, 111, 001101. So it's what we were expecting, but it was backwards. Again, if we go back to the slideshow, we find out that also each symbol is sent least significant bit first. So they're actually purposely sending it backwards. So that makes sense. So we actually are seeing what we saw here, 36 bits training, this signal sent backwards, and then if we continued on, we'd look at the next 6 bytes, convert them using that 4 to 6 byte conversion thing to figure out what they are and figure out our message length, and then go look at our data. So that's kind of how we'd go through decoding this signal. You saw I was cheating because I already knew what library made it, and that's kind of how you'd have to approach a lot of signals that you don't know. You know, try some of the decoders people have already built, but if not, if you're just getting that data, it's like, how can I analyze that data? What does it look like it's doing? Those types of things. So that's kind of first steps into that process. If you get into this, there's a thing out there called the Signal Identification Wiki. So if you find interesting signals, this is a website that has not only a picture of what the waterfall for that signal might look like, but also actually has audio clips of them. So you can, you know, if you're listening to it through GQRX, you can pop over here and say, does it sound the same? Because each one sounds a little different based on its pattern and things like that. So that's kind of cool. It also gives you the frequencies, so you kind of match that up. The next phase, and the other tool I want you to be familiar with, is a tool called GNU Radio Companion. And what that is, I don't have it open. Do I have it open? No. So it's kind of a graphical tool that includes building blocks for building all these different parts that I was talking about. So your radio signal comes in, you need a filter, you need a decoder, you need different parts to it. And that's what GRC does for you. So give you a little more background to this tool and kind of how to use it, because there's a couple gotchas when you first start to use it. So it works by blocks, and all your different blocks are over here. So you can search to find the block you're looking for. So if I need an AM demodulator, I could put that here, and I could just basically, this AM demodulator would basically turn an AM signal, like an AM radio station, more or less into an audio signal. But you drop your source block, and then you drop the other blocks that people much smarter than me tell me which ones to use to, in this case, filter to get the frequency I'm looking for. One of the other interesting gotchas, you see these different colors. You join the blocks by clicking on this one and then clicking on this one, it creates an arrow. But it'll only do that if they're of the same data type. So these blue blocks are of a complex data type. These orange blocks are of a different data type. And that's something we can actually set on some of the blocks, like what type of output is it going to give. But you can only join them together if they have the right data type. And if they don't, you're going to get little red errors. Like I got an error here because I've added something that's not joined, and you can see it's got two different input and output data types. So I'm not great at using this tool, and I'm not a radio engineer by any means, so I have to rely a lot on other people. Someone else had built this exact flow for analyzing this type of 433 megahertz AM signal. Once it's built like this, I can go and execute it. And I think because I've got GrrCON open, it's probably not going to let me use it. So let's close this and close that. It probably gave me an error. And I'm going to try this demo one more time, and then we're just going to move on. Because this is the flakiest part for me. There we go. So if I tune things right, ultimately this would show a scope plot that will actually show in the PowerPoint. Which would look something like that. Like we can actually get to the actual radio signal, view it in GrrCON, and potentially add on additional blocks to decode it. So that's kind of to be aware of that tool, what you can do with it. So some of the key lessons learned, I've got a few more things to come on this after this. Some of the key lessons learned are that hitch to unload the kernel driver on Linux and Windows. And the other thing, you might have seen it there, is you can only really have one tool associated with your radio at a time. So even though GrrCON wasn't receiving data, it had still grabbed hold of that USB device, and so GRC couldn't use it. I had to close the one tool to get the other tool to use it. Or if I'm using command line tools, I got to close the other tools as well. Antenna matters. I didn't get into antennas, but there's a lot of theory about antennas out there. It does make a difference. I have an old TV antenna in my attic, and that works really well for a lot of the receiving I do. So it doesn't, have to be the biggest, highest end exact antenna, but it does matter. Virtualization doesn't work well or at all. I certainly tried this at first running virtual machines, so I could install the software and all that, and the amount of data that's flowing from the USB port into the virtual machine and the need for that to be very right on time, makes virtualization not work. So I run it natively on your hardware. And then it can be a frustrating type of project to get into because a lot of the stuff is very new. People are writing new tools every day, and so if you see a demo that someone created 6 months ago, it might not work right for you because the command line parameters have switched in the tool or different things like that. And then I'm going to ask for questions, and then I'm going to do, after questions, do a quick demo of receiving pager traffic. I want to do that after because we're going to stop the recording because there might be sensitive data in the pager traffic. So just a few minutes if people have questions. Question was, would it be possible to utilize this with an RFID tag? So this dongle, no, because it doesn't get that low of a frequency. If you go out to AliExpress, you'll see these dongles for like $10. You'll also see like about $30 devices that go down to 100 kilohertz, which should be able to do 125 kilohertz RFID tag, or the high frequency like MyFair RFID, the 13.6 gigahertz, something like that. So you can do it with software-defined radio, not this one. Other questions? How do you find a frequency in the first? So the question is there a way to find the frequency in the first place? There's some scanner software out there. You tell it, look in this range and tell me where interesting frequencies are. I haven't tried using it too much. I use GrrCON and just kind of know I'm in this range and then start looking visually on the screen at what's there. But there is some tools out there to do that, scanners. Question is, have I tried this with key fobs for cars? I have not done it myself, but I've seen videos where people have, and it's pretty straightforward. Sorry, I can hear you. The chip that's in this thing can't go down that low. The $30 devices that I was talking about the question was, can the chip go as low as RFID tags? The chip can't go as low as RFID tags. The devices out at AliExpress that are $30 that can go that low have additional circuitry that knock things down so that it kind of works. One more question back here. The question is there software capable of frequently hopping, like your algorithms? The basic stuff that I've used here, like GrrCON, I don't believe has any features for that. I'm pretty confident that GNU Radio Companion likely has some modules that can do that type of thing. Software-defined radio can. I haven't gone down that path. A lot of the protocols that I'm using in the up to 1100 megahertz range don't often use that. That's more often used by your Bluetooth and things like that at the really high frequencies. From my experience, I don't actually know it that well. Good question. All right, you can keep the video going for now so people can see how this works. But then before I start collecting data, we'll stop the recording. So the last thing I want to do is show you pager traffic, and this is extra interesting because I was surprised. I saw this demo at DrrCON a couple weeks ago. How much sensitive data there is in pager traffic. Because it's really just used by hospitals and stuff nowadays. And it's also an interesting demo of how this works as well. I'm going to click enter and, well, okay. So how this works is I've got two utilities. The first one is RTL_FM, which just grabs the data from the RTL dongle, assumes it's an FM radio signal at 929.56 megahertz, and outputs that as an audio stream. That audio stream goes to Multimon-NG, which is a utility that decodes protocols like POCSAG and FLEX that you see here, which are pager protocols, and then it writes the output to my screen. Let's stop.